In this video, we're going to develop the area model for multiplication and division from the concrete and semi-concrete and connect it to the abstract representation as we go. To do that, we're going to put the problems in a context because it's helpful to put them in context. And so for this context, we're going to use this problem that's on the screen. A rectangular playground measures blank feet by blank feet. Determine the area of the playground. Show your thinking. So in this case, there are 4 sets of numbers along the bottom here. This is a great way to differentiate your instruction because different students may start out with different sets of numbers depending on where they are with this. And they would put the first number in the first blank and the second number in the second blank. So for our example, we'll take the 12 and 13. And so we're going to say measures 12 feet by 13 feet. Determine the area of the playground. So what I'm going to do is I'm going to use base 10 materials to build that. We have 12 feet, so I've got 12, so I'm going to build a 10 on one side. And this mat for multiplication is very helpful because what we can do is we can build the factors on the outside of the template, and inside here we'll have our area that we can count up and see the total area. So one factor is 12 feet, and the other factor is 13 feet. So I'm going to build the 13 up here. 1, 2, 3, so 13 feet. So I have 12 feet by 13 feet. And I want to know the area of this playground. So I need to build in this rectangular area here. So I need to think about what size pieces may help me. Here is 10 by 10, and so 10 times 10 is 100, 10 by 10 is 100, so I could put a 100 piece in there. Now here I have 2 units by 10, so I'm going to use some tens pieces. I'm going to put one of them there and one of them there. So I'll build up that area. I need to look over here. I've got 3 units by 10 units down. So I'm going to use tens pieces. 1, 2, 3. And then here, I can't put any tens pieces, so I'm going to have to use my units pieces in here and fill in that area. 1, 2, 3, 4, 5, and 6. So when I build that area up, I see that I've got on my 12 by 13, my total area in here. I've created a rectangle, and now what we need to do is add up those pieces. So this piece from the 10 by 10 was 100. How many tens do we have? We have 1, 2, 3, 4, 5 tens, and if it's helpful to maybe separate it out just a little bit to see those different pieces of the tens and the ones and the hundreds. So I have 5 tens, so 50. And then I have 1, 2, 3, 4, 5, 6 ones. So my total is 156. Now in the context of this problem, thinking about Math Practice 2, we need to put it back in context. Our problem here was 12 feet by 13 feet, which makes this 156 feet squared. It is not feet, it is square feet, because we are 2-dimensional. Feet times feet is square feet. So our units change from feet to feet squared. So this is a concrete way to do that. You can develop this starting with the 4 and the 5 and then move to the 10, 10, 12, 13, and 24, 25 as multiple examples of increasing complexity. And it also kind of depends on what grade you're in and what level your students are, where they may need to start out. So problems like this, where you have a selection of numbers, is a great way to differentiate instruction. So now, let's look at this from the semi-concrete point of view. So now, in the semi-concrete, we'll start out with using gridded paper to help us. This base 10 grid paper. And the way it's set up is that you have a 10 by 10, like your base 10 materials. And every 10 units you see a bit of a darker line to indicate a group of 100 squares in there. And so this is a great way to kind of connect from the base 10 concrete materials, which use these pieces, to a semi-concrete, a drawing, a pictorial representation, because that big piece is represented in here, and each of these tens is one of those. And each individual square is one of those. And so this is a nice transition to help make the connection from the concrete to the semi-concrete. So we'll take the same problem and let's see what it looks like this way. So a rectangular playground measures 12 feet by 13 feet. Determine the area of the playground. So what I'm going to do is I'm going to come down here and I am going to, just using my pencil here, I'm going to mark off 10 and 2 more is 12 down that area there, or that length there. 13 across, so here is 10 and 1, 2, 3 more across to there. So this side, and I can even trace that in a little bit darker, there is 12. And over here I have 13. And so now what I want to do is I'm going to construct this rectangle. So I'll just kind of complete the other sides of it here. And then I can shade in all of that to help me kind of see what the whole area is, and therefore what is the product of those numbers 12 times 13. So when I look at that, these darker pieces here kind of help me see where the breakup is of the hundreds. So in this section right here, I have 100. So there is 100 right in there. This is 10, 20 right here. Here is 10, 20, 30 right here. And down in here, I have 6 units. So then when I go to find my product, I add all of the pieces together. So I have my 100 plus my 20 plus my 30 plus my 6. So 156. And again, in the context of this problem, think about math practice number 2, putting the math that we pulled out back into context. We're going to have 156 square feet. And that's important since our units were feet in the beginning. We want to be sure that we attend to precision, math practice 6. and add our units in correctly at the end of the problem. So this is a semi-concrete way, because you've got all of the grids in there that you could count, that students can count, and so on, and they can draw this. A more abstract, yet still semi-concrete way to do this problem is to put the same problem on plain paper and create an area on plain paper. And so the next step of this sequence would be to just construct an open rectangle. Because I know I have a rectangular playground. On one side it measures 12 feet, and the other side is 13 feet. What is the whole area? So now what I could do is I can use some of the reasoning that I learned previously and break this 12 into 10 and 2. Kind of like what I did before. And I can break this 13 down. I can decompose it into a 10 and a 3. And now I have 10 times 10 is 100. 10 times 3 is 30. 2 times 10 gives me 20 in there. And 2 times 3 gives me 6 units in there. And so when I add all of these pieces together, 100 plus 50 plus 6, I get 156, and we are square feet. This part over here is what's known as partial products. This is how you develop the concept of partial products, so that in the abstract we could take 12 times 13 and think of it in terms of the 10 times this 10 is 100. 10 times 2 is 20. There it is there. Then take the ones, and the 3 times the 10 is 30. There it is. And the 3 times the 2 is the 6. And I add all those together, get 156. If we want to move this even further into the understanding of the standard algorithm, 12 times 13, yet still using the partial products, I could start with the ones. 2 ones times 3 ones is 6 ones. Then 3 ones times a 10 is a 30. Boom, boom. 10 times 2 is 20. Boom, right there. And 10 times 10 is 100. Right there, I have that. And I add all of those together, and I get 156. Again, in the context of this problem, these are all going to be square feet. So the area model is a nice way to develop towards the standard algorithm eventually. Working from the concrete with the base 10 materials to the semi-concrete with the base 10 grid paper to the open area model, which is still semi-concrete but very symbolic and very abstract, to the completely abstract symbolic representation. So that's the area model development for multiplication. So let's look at why it is important to develop the area model. So let's just take an example, the problem 18 times 23. So in the area model, we'll just use the open area model. So I'm going to construct an open rectangle. This side is 18, so I'm going to decompose that into 10 and 8. This side is 23, so I'm going to decompose that into 20 and 3. And when I do that, And it doesn't matter, I could do 10 and 10, but I'm going to just do 20 and 3 here. If I look at the pieces of the rectangle and find the separate areas, this is 200, this is 30, this is 160, and this is 3. So that if I add all of those together with my partial products, excuse me, this is 24. If I add all of that together with my partial products, I get 414. In middle school, students are going to have problems that look like this. 2x plus 3 times x minus 5. An area model will also help them. If we think about an open area model, this side is the 2x plus 3, and this side being the x minus 5. We'll decompose 2x and the positive 3, and the x and the negative 5. We can think about it just the exact same way. 2x times x is 2x squared. 2x times negative 5 is negative 10x. 3 times x is 3x. 3 times negative 5 is negative 15. If I think about it here, I've got 2x squared for my area. Negative 10x plus 3x is negative 7x. And then minus 15. It's the exact same model that I can use to develop these types of problems. The property that you're working on and developing is called the distributive property. Students begin to work on and become familiar with the distributive property in elementary school. They expand on that in middle school through working more algebraic types of problems. Let's look at this a different way. If we do this purely in the abstract, thinking about the distributive property, we had 18 times 23. We decompose the 18 into 10 plus 8 times 20 plus 3. And what we did is we said the 10 times the 20, we got 200. We said the 10 times the 3 and got 30. We said the 8 times the 20 and got 160. And then the 8 times the 3 and got 24. And then we added all of our pieces together and got 414. For this problem, in the abstract, it's very similar. 2x plus 3 times x minus 5. We take the 2x times the x and got 2x squared, which we see in that box. The 2x times the negative 5 and got negative 10x right there. The 3 times the x and got 3x. And the 3 times the negative 5 and got negative 15, which is right there. We combined our like terms, so we added all of our partial products together and got 2x squared minus 7x minus 15. It's the exact same thing that students begin in elementary school with this area model of multiplication that they extend into algebra in the middle school. It's so important to teach the area model at both elementary and middle school. It gives a much deeper understanding, because here's one misconception that happens along the way in middle school and in high school. As students go to multiply these using the distributive property, oftentimes students may multiply the first term, the 2x, times each of these and forget about multiplying the 3. Having this area model here as a way to visually see the multiplication for this problem, they will be sure to add all of the partial products together to get the correct answer in the end. So now let's look at the area model for division and develop it from the concrete and semi-concrete, connecting it to the abstract representation as we go. We'll start this one out with a context, just like we did the multiplication. We have a playground again, a rectangular playground, and it measures blank square feet. One side is blank feet. Determine the length of the other side. Show your thinking. So we have some sets of numbers at the bottom that we can use. Again, it's a great way to differentiate instruction. Let's just start out by using the 42 and the 3. So measures 42 square feet. One side is 3 feet. Determine the length of the other side. So here's what we know. We know, and if we're going to think about this in terms of multiplication, I'm going to use this template again that I used before. I know that I have 42 units here, square feet in this case. And one side is 3 feet. So what I have to do is think about, well, what does one side kind of look like? So I'm going to put 3 units over here because I know that one side is 3 feet here. And basically what I need to do is figure out what the other side is. So I have my 42 here, and if I think about it, I could kind of take 3 of these 10s and put those right there. And I've got this much left. I have 12 left. I can only go with 3 on one side. So I need to trade out this 10 for 10 ones. So that's what I'm going to do next. I'm going to trade out my 10 for 10 ones. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm going to trade that out. Now I can use these, and I'm going to continue to build my rectangle here. So there we go. So we have that. So what is the length of this side? Well, we have a length of 10 and 4 more. 1, 2, 3, 4. So the other side is 14 feet. So what does this look like? Well, if I model this and show my thinking here, I had 42 to begin with, and on one side I had 3. So how many were on the other side? Note, this is a nice way to begin for students to recognize and see division written in this way, because this models this in the abstract. So here I had 10 and 4 more. So I had 1 10 and I had 4 ones in length. So 14, and being precise, we're going to add feet. We're going to attend to precision, thinking about math practice number 6 as well. So that's the concrete. And you can try other problems the same way. Let's look at semi-concrete now. So I'll move these, and we'll take the same problem, and we'll just look at it in terms of a semi-concrete. And I'm going to use the same paper that I used before. I'll just fold it over there a little bit. So 42, and I'm going to start out with one right here on the corner, so I can see and begin not in the middle of one of these blocks of 100, but right on the edge. So I know I have 42 square feet total. One side is 3. So I'm going to build down 3 feet that way. And I have 42. So if I come over this way 10 and shade those in, that gets me to 30. But I know I can only shade groups of 3 here. So there's another 3. So I'm at 33, 36, 39, 42, and 4 more. So that side was 3. This is 10 and 4. So the other side then is 14. Let's do that same thing, and let's use a different problem. Let's use the 117 and 9. So in this problem, our playground now is going to measure 117 square feet, and one side is going to be 9. So we'll come down here and we'll do the same thing. We'll start right here. And I know one side of this is 9, so I'm going to mark off 9 right to there. And I know I have 117. So if I shade down groups of 9s here, I can shade 90 of these. This is 10. And so I know that this in here is going to be 90. And I may even want to write that as 90 in there so that I kind of keep track of where I am all the way down to here. Let's do another 9. So there's 99. And another 9 is 108. And another 9 is 117. So this side, here I had 27 total, which 90 and 27 is 117. So if one side is 9, the other side has to be 10 plus 3 more, 13. So in this case, the length of the other side is going to be 13 feet. And I've shown my thinking by drawing this diagram here. If we take this now to the abstract and look at the open area model for division, so let's see what that'll look like. Let's take this third problem. 315 are the two numbers. So now I know that my playground is 300 square feet, and one side of it is 15 feet. Determine the length of the other side. So I can take what I just did, the understanding of the base 10 materials, next step being the base 10 paper, and now to a completely open area model where I'm going to draw a rectangle, because I know I have a rectangular playground. I also know that it's 300 feet, but I'm not sure how that's kind of divided up yet. I know one side is 15 feet though. And so with my understanding of how things have worked with base 10, I can decompose that into 10 and 5. And so what is the other side going to be? I know I'm working with 300 here, square feet, as my total. So if this side is 10, I can put 100 in here, and 50 more of it's going to go here. So there's 150. Well, if I do that again, another 10 is going to get me another 100 and another 50. So there I have 100, 250, 300 square feet. So the other side is going to be 20 feet long. So in this rectangular garden, it's 15 feet by 20 feet long. Students can use whatever facts they know as they're building up this area model. Tens, that decomposition into tens and plus 3 or 4 or 5 tends to be one that students work with pretty well. They may use others, and that's okay. Whatever works for them to decompose the number and to build the area or to break down that area into the two lengths for division problems. It's helpful to have a context to put the problems in so they can kind of think about what is the math behind it, but in terms of a context. Because if we just say, what is 300 divided by 15, that's not as helpful as saying you've got a rectangular playground. Let's start out with that, a rectangle, a shape that we know. One side measures something, what's the other side? And build off of that. That really helps to develop the math. We're working on math practice 2 because we're pulling the math out of the context problem. We're doing some math, and then we are putting it back into the problem with the proper units and so on, attending to precision as well. So we're working on math practice 6 at the same time, as well as other math practices. We're connecting representations here of in this case, the pictorial or the semi-concrete to an abstract. And we can begin to develop from here now the standard algorithm for division.